Okay, so I'm going to start with chapter 7, and I'm going to do question number 22, which asks, express the units of the force constant of a spring in SI fundamental units. So, so the constant of a spring, which is K, that is Newton meters normally, and so the equation for K usually is Fs equals Kx, and we know that Fs is newtons because it's a force, and X is is meters because it's a distance. And so if Fs equals ma, which is newtons, equals kg times meters per second squared. So I can plug in these SI units into here, and then like solve for K. And so I'd get, in which case I'd divide both sides by m. So I would get kg times meters per second squared is equal to K times m, which is as in mass, not a variable. So then I get that K's SI fundamental units is equal to kilograms. Well, the masses cancel out, so it'd be kilograms per second squared. So for chapter 8, I chose question number 3. So it says a block of mass of 0.25 kilograms is placed on top of a light vertical spring of force constant 5,000 newtons per meter and pushed downward so that the spring is compressed by 0.1 meters. After the block is released from rest, so that means that VI is 0. It travels upward, then leaves the spring. To what maximum height above the point of release does it rise? So dy is equal to question mark. D is in distance. So, alright. If this is like the diagram, and it's normally, so this is x, let's just say that it's compressed to here. That distance is x. So I'm going to say that so work equals first times distance, and work equals change in total energy. And okay. So I'm gonna go with that kinetic energy maybe is equal to potential energy. Like, oh wait, my bad. That's it. Okay. PES equals PEG. Alright, so change in total energy. So since it starts with the spring compressed, there's PES, but it's at rest. So there's spring potential energy at the beginning, and at the end the spring is no longer compressed and it reaches its max height. And at its max height, because it'll be changing directions, it's also at rest. So that gives it maximum gravitational potential energy. So in that case, I'll just plug in. This is mgh, and this is 1/2 mv kx squared. So I can just plug in and find h. So with that, let me roll this up. So I could just do 1/2 k they gave us was 5,000 Newton meters times 0.25 kilograms squared. And that's equal to 0.25 kilograms times negative, well, just pause it, 9.81 because it's gravity, meters per second squared times h, which is what we're looking for. So I'm going to plug this in and divide. Calculator, okay, so my calculator seems to die, but I have a backup. Okay. 0.5 times so on this side we have 156.25 divided by so that equals 63.7 meters, and that is how high it goes. So I left the sound on my computer, but it's just the questions that I chose. So I just want to acknowledge that I'm not cheating. Alright. So for chapter 9, I chose question number 2. And it says an object has a kinetic energy of 275 joules and a momentum of magnitude 25 kg times meters per second. So find the speed and mass of the object. So I'm going to write down the equations first. So I'm going to isolate momentum in this equation so that I can just plug in and find a variable through that. So I'm going to have to square mass, and in order to not have to add to this side, I'm just going to do times 1, so I can just not have to multiply it. So I have K equals 1/2 m squared v squared over m, which I can plug in p, momentum, and get K equals 1/2, I guess it could be 1 over 2m, and I'll have p squared. Get rid of the 1, okay. So I can just plug in here, and I can just have 275 joules is equal to 25 kilograms per times meters per second, and then square that over 2m, and m will be my variable. So I'll just cross multiply, and I'll have 275 times 2 is 550 joules times mass, which is equal to 25, well, I guess I'll square that. 5. So that's 625 kilograms times meters per second. So from there I can just divide by 550, and I will get that mass is equal to 1.13 kilograms. So from there I can just plug in to P equals mv. 25 kilogram times meters per second is equal to 1.13 kilograms times v, and v will be my variable. Divide, and I get that v is equal to that v is equal to 22.12 meters per second. Those are my answers for chapter 9. Okay, so for chapter 10, okay, so for so for chapter 10, I am doing question number 15. So it says that a racing car travels on a circular track I'm just going to draw that out. With a radius of 250 meters. Assuming the car moves with a constant speed, so we know, okay, well, yeah, constant speed. Okay, velocity is 45 meters per second. Find its angular speed and the magnitude and direction of its acceleration. Okay, so it's going to be AC because it points inwards. Okay, because it's a circle. So I'm going to start by finding angular velocity. So the equation for that is that V equals angular V, what is it, omega R, I think. And so I can just plug in. So that is just 250 meters times angular velocity, or speed rather, which is equal to 45 meters per second. So I can just divide 250 on both sides and get that. The angular speed is 45 divided by 250, and I would get 0.18. What is it? Rad per second. Okay, and so then from there, I would find acceleration. It's just FC equals, actually no, my bad, AC equals V squared over R. So I can just do 45 meters per second squared over 250 meters. And so if I plug that in, I get that the acceleration is equal to 8.1 meters per second squared. Okay. And once again, it's just like the questions. Okay, so for my last question, chapter 11, I'm doing question number 24, and it says, show that the kinetic energy of an object rotating about a fixed axis with angular momentum L equals I omega, once again I think it's called omega, can be written as K equals L squared over 2I. So this is very similar to the one I chose before, so it's just KE equals KE, or K they wrote, well, it's actually 1/2 IW squared, but I want to make it so that I can, what's it called? So I'm going to take L equals IW and isolate the W, so it's W equals L over I. And then from there, I can, what's it called? Okay, okay, yeah. So I want to plug in, what's it called? W here, I think. Okay, yeah. So we have K equals 1/2 I, and plug in L over I squared, and so I can also just distribute the squared, I guess you could put it like that. So I'd have K equals 1/2 I L squared over I squared, and then you cross cancel that out, so then I have K equals L squared over 2I. And so that is how I can prove, I guess, that kinetic energy written out like this can also be written out like K equals L squared over 2I. Alright.